Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Daniel Bamberger with us today. Hello, Daniel.
Hi.
Let's see. Well, thank you so much for agreeing to talk about your very lovely article, which we'll get to here in a second.
Mhm.
But let's see. What's your geolocation, Daniel? Where are you at?
Yeah, I'm in Germany.
Very good. What part of Germany?
Yeah. Marburg,
Okay.
about an hour north of Frankfurt.
Very cool.
Right.
All right.
Right in the middle.
Yeah, mid-Germany. Excellent.
Yeah,
So
yeah.
let's see. It is August 20th of 2025 as we record this. And how is late summer doing in mid-Germany?
Yeah, it's a lovely summer evening. So,
Is
I
it good
think,
for observing? Is it good for observing?
yeah, we've got our telescope, our observatory in London. So, I would have to check the weather in London right now. But it's really beautiful outside. I'm gonna step outside later and just have a look.
Very nice. Very.
Maybe, yeah.
And I'm in Phoenix, and yeah, we're hot. That's about all I can say. We're
Oh,
probably
yeah.
up in the 40 C's today, 41 C's today. So it's a little on the toasty side, but it's lovely. So yeah, very good.
Yeah,
Uh,
nice.
let's see. And Daniel, what do you like to do for research?
Well, most of my time I spent observing near-Earth asteroids. Um,
Cool.
yeah, just follow up the the stuff we do at our telescope.
Uh-huh.
But I also got some uh, interest in just the dynamics of our solar system,
Uh-huh.
which is what our paper is about.
Yes. Very,
Yes.
very good. And that is going to bring us to this. Very awesome. Not this yet. We want this over here to start. Research
Yeah.
notes. It is open access. It is the open access era, people, and you can go grab a copy for free. Go get one.
Yes.
A minor planet in an outer resonance with Uranus. And Daniel, take us away.
Yeah. So I'm gonna make your screen a little larger. 1 second.
Hmm.
So that's better. Very nice. I can read the names of my lovely co-authors now.
Yes, they are lovely.
Yeah. So as you can see, I'm in Germany, but my co-authors are not. It's quite an international cooperation. Two
Hmm.
from the USA, one from Brazil.
Oh, cool.
Um, Mostly undergraduate students of astrophysics, astronomy.
Very
Yeah.
nice. Very good. Good shout out. Good international collaboration here. Okay, let's roll.
Yes. Yeah. So you have a look at the abstract just to give a drive of what we were doing.
Uh-huh.
So this has started with us locating some precavalry observations of a recently announced centaur,
Hmm.
this asteroid 2015 OU-194,
Okay.
which, when it was announced, had an observation arc of exactly 1 year.
Convenient.
And we were able to extend that to 3.5 years,
Yeah.
finding that precavalry, which allowed us to do some simulation.
Nice.
Because with that 1 year arc, the uncertainty really was too
Yeah.
large to say anything at all about that object,
Hmm.
other than that it's in a bit of an unusual place, which prompted us to look in the first place,
Yeah.
because it was close to a region between Uranus and Neptune that is either at the 2 to 3 resonance with Neptune
Okay.
or the 3 to 4 resonance with Uranus.
Okay.
And we thought this could be either way. And we thought probably Neptune, but when we did some simulations, we found that it's currently in this resonance with Uranus,
Nice.
which was a bit of a surprise because we were not aware of objects in any such resonance.
Hmm.
And as it turned out later, that was because none was known. Um,
Discoveries are
so
nice.
yeah, so this that was the point where we thought, this is This is an
Write
interesting
it up.
find. Yeah,
Hmm.
probably worth talking about. Um, so this region between Uranus and Neptune is really um, one that's got a lot of very unstable orbits. So you have lifetimes that are really, really short, on the order of tens of thousands of years. But this object is going to remain in that uh,
Wow.
region for resonance
Cool.
um, from at least 1 million years in the past until at least 500,000 years in the future.
Wow.
Um, there's some indication that it entered that resonance at about minus 1.1 million years.
Okay.
And there's some indication that it may leave maybe about 600,000 years in the future.
Yeah.
But really, at that point, the orbit becomes undetermined,
Okay.
and there's a chance this resonance could survive millions of years. Um,
Okay. I'm with you.
so we were looking for other objects
Yeah.
in a similar orbit. Didn't expect to find one, and found one, of course, as these things go.
You must
So
look.
it turns out that there was another object, 2013 RG98, known for a bit longer,
Mhm.
that
It's really
showed quite similar behavior.
okay.
A bit, a bit. Uh, there are some differences between the two, which we're going to discuss further down. But we really have two objects in that orbit class now,
Nice. Very good.
and our search for candidates brought up a third candidate
Hmm.
that had this behavior we expected in the beginning, this chaotic influence of Neptune, Uranus, jumping back and forth between influenced by the other, influenced by the former,
Okay.
which is a bit what we expected to find, and it was nice to see that this kind of stuff exists.
Yes. Yes.
Would would have been a bit surprising. So if you can go further down,
Sure. Very nice.
gonna
Okay.
we're gonna just get a little introduction.
Hmm.
Um, some of this I've said already that we are in a really chaotic region of the solar system.
Hmm. That sounds
So but if you go further out, you've got the trans-Neptunian region. There are lots of objects, lots of resonances, very stable, very interesting,
hmm.
um, very cool.
Yes.
If you go further in to Jupiter and inside, you've got lots of objects. You've got not so much resonances, but the Kirkwood gaps, the gaps in the asteroid
Yes.
belt,
Yes.
which are strongly influenced by resonances. So you've got two regions of the solar system where you have a lot of um,
Small bodies.
behavior of this nature,
Hmm.
and then this gap between um, mainly Saturn and Neptune with almost nothing.
Yes.
Yeah,
Yes.
because mainly Saturn and a bit the fact that Uranus and Neptune are themselves in a near resonance.
Uh-huh.
This makes orbits in that region quite unstable. There is a region to the inside of Uranus that has some known resonant objects. That's the last paragraph of the introduction.
Uh-huh.
You have a few known objects in a 5 to 4 resonance with Uranus on the inside. You've got one in a 4 to 3, um, but really nothing on the outside.
Nice. Okay.
So
I'm with you.
uh, the the
Hmm.
paragraph before that is just definition. That's the usual definition you have of
Me no
resonant
residency.
objects,
Uh-huh.
um, where
MMRs.
you where you define a certain criterion that tells you uh, what needs to happen for an object to be classified as resonant. So you've got the resonance angle, which
Hmm.
has to librate. That means to oscillate and be bounded between values smaller than a range of 360 degrees.
Cool. Very good. I'm with
All
you.
right. So let's go to the second
Okay,
section.
observations.
Yeah, that's where
Mhm.
it gets interesting. So this object was announced in May with a very short observation arc, which was then
Okay.
published in June in an MPEG by the Minor Planet Center,
Yes.
which is where we learned about the object and noticed that this is a region where we don't see much. Let's see what we have here.
See what we got.
And yeah, let's see what we got. And so this object originally had observations from Mauna Kea, TO9,
Mm-hmm.
so observatory called TO9,
Uh-huh.
that spent exactly 1 year, 2015 to 2016. So these are quite old. This object was found in observations that were taken about a decade ago
Yeah.
and only noticed,
Once in a
if
while.
you notice now, as things go sometimes,
Yes.
um, people don't look at the images, I suppose. Um, but this 1 year arc really wasn't much to go about when you were looking at simulations longer than a few thousand years.
Yeah.
So we really needed more data.
Mm-hmm.
Luckily, the archive of that telescope of Subaru is available online.
Yes.
So we could just have a look if we could find something.
Mm-hmm.
And indeed we did. So we found some more observations from 2017 and 2018,
Nice.
at which point we had an observation arc of uh, about, yeah, 3.5 years,
Mm-hmm. Yep.
which made for a solid um, data set. And we had a look later at what influence the uncertainty still had. Um, I'm going to talk about that. But at this point, we could really draw some conclusions.
Cool. Very nice.
Um, so we get a little bit of data about the orbit itself.
Mm-hmm.
Um, uh,
23.
34 obs we had 34 observations in total at this point,
Yes.
and a shout out to Bill Gray and his Find Orb software. He's written this lovely little tool used by a lot of asteroid observers,
Mm-hmm.
which can just compute this orbit on the fly from the observations.
There's a link
And
to Find Orb, so check that out if you
yeah,
like.
you get a link in the paper to this and to a bit of other software that we're using later.
Mm-hmm.
Um, so you get an orbital period about 113 years, which
Mm-hmm.
is roughly where you expect the region um, these resonances that I was talking about, 2 to 3 with Neptune, 4 to 3,
With your
3 to 4.
yeah.
Um, and
Nice.
we had multi-band observations at this from Subaru, so we could just have a look at the color of the object,
Mm-hmm.
get some physical data, nothing spectacular, but when you really calculated the color indices, these are just average for a centaur.
Mm-hmm.
So this is not an extraordinary object, probably in its physical parameters.
Yeah.
That's just average.
Mm-hmm. Yep.
So
Gotcha.
then about our simulations,
Cool. Okay.
we
I'm with you. Mm-hmm.
yeah, that's the third section. Um, as I said, with the extended data arc, we were able to characterize what was going on. Um, and um, and for that, we were using a software that I've been using for maybe 15 years at this point to do these kinds of simulations, which is Aldo Beta Janus, Solex, and Xorb package, which is just a lovely piece of software, also freely available. I think there's a download link
Mm-hmm.
in the paper.
Yes.
Um, just a lovely little tool, and probably the only orbit determination software you can find that is on par with JPL's uh, ephemeris, which
Yeah.
is
Horizons.
really quite impressive. So
Very cool.
you can use that software to really do some accurate and long-term simulations, uh, which we did. We took, of course, the nominal orbit of our objects, uh, but we were also concerned what the uncertainty region would be. So we were we would have liked to do simulations of a large collection of virtual clones,
Yes.
but that's not quite the computing power we had available. So we were looking at a pair of clones on either side of the object. It's in the uncertainty region at 3 standard deviations,
Yes. Okay.
just to get
Just to
a
bound it a
feel.
little bit. Yeah. Mm-hmm.
Yeah, just to get a feel for the stability.
Mm-hmm.
Um,
Good.
and comparing those led us to conclude that this object
Interesting.
is in resonance for quite a while,
Very cool.
from about 1 million years in the past until at least 500,000 years in the future. I think I mentioned that this resonance could survive for millions of years, but the uncertainty is not quite there yet to draw that conclusion.
Nail it down. Yeah. Good. Okay.
Uh, yeah, and not only is this main object we found 2015 OU194 um, in this resonance for the entire time, but the angle at which the resonance angle librates, the amplitude is quite small, which indicates that this is more stable than we had expected at such a point in
Oh,
at such an orbit at all. So we've got this long amplitude, but between about 1 million years and 1.1 million years in the past, the both clones start to leave the resonance.
okay. That's interesting. Okay.
So we really can't say anything at this point. The nominal orbit stays in resonance at this point. Both sides of the uncertainty region do not,
Yep.
which is quite funny.
Interesting.
Yes, yes, we really get to a point where we need a substantially longer observation arc, which is possible, of course, because anyone who observes this object today extends its arc to 10 years. So
Nice.
please, if you have a large telescope, 8 meters, 10 meters, have a look.
There you go.
If
There's
if
there's there's a call, people.
yes, yes, anyone with a um, multimeter
Anyone.
class telescope should have a look
Anyone with a
immediately.
10 meter. Okay.
Yeah, yeah. I don't think you need 10 meters, but you need a large telescope for this one.
hmm hmm
Um, so uh,
Good.
as I write here, a sophisticated analysis of that stability region really is not uh, something we were able to do, and probably wouldn't be something to cover in a research note anyway.
Okay. Yeah.
So let's come to that fourth section,
Okay. Additional
the
candidates.
additional candidates. So we were looking for objects first in that general region. Found surprisingly few, 4 or 5,
Okay.
um,
hmm
of which one we could exclude immediately,
Okay.
and but then looking further, we found one object with a really good data arc of more than a decade,
Good.
um, and one object with a very solid data arc of 8 years, and these showing some way more interesting behavior.
There resonance.
Yeah, so that first object, 2013 RG98, turned out to be actually very similar to the object we had identified, which is that it remains in resonance from about 400,000 years in the past until 470,000 years in the future. We
Yes.
just happen to lie right in the middle.
Nice.
Um, but of course, there are a few key differences, with mainly that the amplitude of the vibration is a lot larger for this object,
Okay.
and
Okay.
and we actually found, and we'll see that later when we look at the figure. Um, we um, we found that this resonance actually is intermittent before 400,000 years in the past, which means there's a little time where the object just isn't in resonance. It enters back, it leaves it again, it enters back,
Okay.
and so on. So this is kind of at the edge of where you find that where it enters probably just the right conditions.
Mm-hmm.
Um, and then we have this third object, 2014 NX65, which was a bit of an interesting one. Um, because, and that's probably something that should be looked at again, and we
Wow.
may in the future, because this object is really jumping between
Yeah.
that resonance with Uranus and an inner 3 to 2 resonance with Neptune. Those two resonances lie quite close,
Pinball.
and you get this jumping behavior.
Mm-hmm.
It enters one resonance, it leaves, uh, it rotates, or it doesn't vibrate for a few thousand years, then enters the other one,
Yep.
stays there for a few 10,000 years, leaves, and really very chaotic behavior. And despite that data arc of about 10 years, the region where that orbit stays deterministic is a lot shorter than for the other two.
Okay.
So there's not much we can say about its long-term behavior at this point, but that's some interesting behavior to look at for sure
We'll come
in
back
a
to
in a different paper.
we'll come back to that. Yep.
Yeah,
Mm-hmm.
yeah. So I think if you go down, you go
Oh, we
to
got a
the
figure.
figure. Yeah, yeah.
Uh, all
That's
right,
it.
let's zoom out to get it all.
Yes.
Zoom
So
in.
you've um,
Okay.
that's this is a chart of the libration angle. At the top in red is the first object, 2015 OU194,
Yes.
and the second object, 2013 RG98,
Oh, yeah.
in blue at the bottom.
Uh-huh.
And this is roughly what I was describing. Um, so this chart runs from 1 million years in the past till 500,000 years in the future, yes.
Mm-hmm.
Um, and at the top, you can firstly see the amplitude quite quite a bit lower than the one in the bottom
Great.
chart.
Oh, yeah. Nice.
Yeah,
Oh, definitely. Okay.
it is it is yeah, not perfectly regular. You see some interesting behavior there,
Phenomena, yes. Uh-huh.
which is to
Mm-hmm.
be expected. This is an unstable region of the solar system, and this resonance is not going to survive till the sun goes out, probably. But when you go to that other one uh,
That's
on the bottom, you can really spot these
yeah.
parts where it leaves the resonance. You just get basically a space filling curve.
Yeah, yeah.
Uh, you just get a blue wall
Oh, yeah, blue wall. There we go.
because that oscillation you see there just turns into a graph that shoots off.
Mm-hmm. Interesting. Very cool.
Yeah, that's a nice tool to just quantify resonant behavior.
Mm-hmm.
Nothing new. We didn't invent this kinds of stuff.
Yeah, yeah.
Um, so the data for this and uh, anything we use to create that plot is available for download.
Nice.
So you have
Ah, here we go.
some auxiliary data
Mm-hmm.
to play with if you are so inclined and
Cool.
don't want to do these simulations on your own.
Good, 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 good. Data sharing is always good.
Yeah, it's
Okay.
especially because there is no telling that the nominal orbit that you arrive if you repeat this and determine an orbit yourself is going to be the same nominal orbit that we got.
Okay.
So, yeah.
Mm-hmm.
But I'm quite sure that at least the time range we covered here is going to be safe.
Good.
Fe- Yeah. So I think we got to the conclusions, which is just a repeat of what I already told you.
Uh-huh.
Um, we have
Okay.
yeah, a unique kind of object,
Yeah. It's great discovery. Very good.
and that unique kind of object immediately turned into a family after a few minutes
Well,
because we found a second one.
once you find one, there's usually more.
Yeah, it's
So very
which really begs the question why nobody was checking for that other one before. I don't know.
that's hard to say.
I know that people have been looking for stable orbits
Mm,
between Uranus and Neptune.
yeah,
There are some interesting papers, but really nobody was specifically looking at that region. So
beautiful discovery. Beautiful
yeah,
discovery.
really nice, uh, more or less coincidental find.
The best kind. Serendipitous.
Yeah,
Very cool. Very cool. Daniel, I want to thank you so much for walking us through your
yeah,
very
my pleasure.
research note. Very nice.
Yeah,
Very nice. Let's see. And you kind of touched on it a little bit there toward the end and in the middle too. So let me ask, where do you think we go from here, given the published article on this object? Are there additional observations one might want to make with a 8 to 10 meter class telescope? Is there additional theoretical calculations that could be done? So what do you think are the next steps? Where do we go from here?
yeah. Something that's that would really be nice would be if someone recovered the object. I already said. I'm
Yes,
gonna repeat it in case
absolutely.
people forgot it.
Yeah, yeah.
Um, so some more observations, and really, the moment the Vera Rubin Observatory is starting,
Hmm.
we hopefully get to see a lot more of these. So these two objects are hopefully gonna become 10 and
Nice.
maybe more. And
Nice.
I would really hope to for someone to find an object in an orbit that's not stable just on this million-year time scale, but possibly primordially stable.
Ooh, okay.
So an orbit that's been stable for the lifetime of the solar system.
Nice. Okay.
That would be a nice find.
Cross fingers.
But that's a very Rubin hope. Another thing for us that I've been thinking about,
Yes.
and I've shared that with you beforehand, is a little project I've been working on with a friend
Uh,
from Texas.
uh-huh.
That's
Yeah, wrong one here. Let me pull everything up.
yeah.
Um,
Maybe
da-
if you can open that GitHub,
yeah,
so I
yeah.
can show people what they can get and play with.
Give me 1 second. And boom, and a little slow here. Bang. Okay.
People can see it. All right.
Yep.
So that's a little tool I've been working on with my colleague Maja uh, Kapovic,
Uh-huh.
which is
Keep going.
I yeah I'm gonna bring that up here so I can I can look at it too.
Mhm.
Um, I mentioned to you that we've used that Solex and Xorb software. which
Yes.
said is a lovely and really very powerful tool, which is true, and we're gonna keep using it. Um, but really, it's not designed to run simulations on this extremely long time scale.
Yeah.
So
Rebound.
we we would really have like to speed that search up. So
Okay.
well, when we were looking at that resonance and were trying to confirm that instant resonance, we were really limited by our computing power. And the reason we had to limit us to three object to two clones plus nominal per object really was a time constraint
Okay.
because these simulations take
It's
quite
take
a
a
long
while.
time,
Right.
on the order of hours per object,
Okay.
um, many hours per object, which really was not feasible for the number of clones we really would have needed. So what we were looking at are two things. One is a visualization tool
Yes.
for visualizing resonances. We're gonna show the user some animation soon. And the other part was something I thought we'd be working on, which is try to automatically identify resonances.
Okay.
Um, as it turns out, someone beat us to the second part,
Okay.
which is really nice. Someone, yeah, Smirnov, who was so kind to share his program on GitHub with a license we could just fork and use ourselves. So great work, very nice.
Good shout out.
Yes, yes, that's a really cool software. Just called Resonances, and what it does is it is able to pick orbital elements from the internet, from the database, and immediately identify two-body mean motion resonances,
Good. Okay.
three-body mean motion resonances, which is quite exotic. Um,
Yes.
even identify intermittent resonances.
Cool. Very nice.
Yes, that's a really impressive kind of software. So what we did, we are
Good.
of course adapting that a bit and then concentrating on that visualization part. So Maya has created a little animation for me of the object that I had been studying. So this is starting about what I think 1.3 million years in the past.
Mm-hmm. Yeah.
And you can see it at in the beginning it is rotating, and right about here it snaps into that resonance,
Right. That's that
and
180.
then you get this oscillation.
Uh-huh.
Um,
Cool.
the You've got Uranus in blue kept in place
Mm-hmm.
on the horizontal axis,
Yes.
and the orbit of the object um,
In yellow.
in that resonance. And if you we could keep that running for a long time. This specific orbit, I think, remained in the resonance for about 2 million years in the future.
Wow.
So as I said, 500,000 years. That's the thing we were confident about. But that resonance really could go on for a very long time.
I think this is the long.
Um,
Whoa.
oh yes, that's the other one, I think.
Yeah, this
Oh,
is the longer one.
yeah, that's the longer one. So if you go back further in the past to about 1.5 million years, it's really um, rotating quite a lot before it again snaps into that resonance and then
And the
stays there for
stability.
many hundred thousands of years.
Ah. Okay.
I don't know if you can open the other animations I've sent you.
Uh-huh.
Uh,
There's this one.
yeah, that's another object in a resonance with Neptune. That's a known object
Okay.
that is known to be in a 4 to 13 resonance.
Okay. Yeah. Okay.
A little bit exotic, but
Yeah.
perfectly stable. The trans-Neptunian region is
Yes.
just just a dream for people who like small fractions and not so small fractions. Um,
TNOs.
and of course, besides all the nice dynamics, you really get some beautiful pictures.
Absolutely.
I think this is almost floral. This is an object
Yes.
people may recognize. That's the dwarf planet Haumea,
Mhm.
which isn't quite in a stable resonance with Neptune, but is in an intermittent 5 to 12. No, not 5 to 12. I think 7 to 12 resonance with Neptune, which it leaves about once every 2.3 million years, only to re-enter a few 100,000 years later, and then repeat that cycle.
Aha.
And it's not running quite smoothly on the screen I see here, but
It's being recorded.
you
Slowly. Don't
you
worry
you
about
can you can really that behavior of periodically leaving its resonance with Neptune is something that has been known for quite a time.
it. Wow.
But you can really get a feel in that animation of what is causing it to enter and leave, which I think uh, is really a nice thing. Not only
Ah, yes.
to maybe use these animations to visualize these to laymen, but I think these are useful even to people who are researching that stuff.
No, some beautiful, beautiful animations that make things pretty clear, and so
And
it's a wonderful
yeah,
tool.
and the creation time for these simulations is reduced enormously. So we started with Solex XORB with a time on the order of hours
Hmm.
per object, and for these from start to finish, you it takes less than 10 minutes.
Nice. That's a nice compression. Very.
And the code is available so on GitHub.
Hmm.
It's in an alpha state. If you try to run it, it's probably gonna break. It's not quite ready yet.
Not right.
There are still quite a few hacks and quite a bit of work to do, but we are working on it. And
Good.
over the coming weeks, and yeah, let's see how long it's gonna take. But that's maybe something we're gonna announce in our next research note. Let's see.
Lovely. Lovely. Very nice. Very nice.
Yeah,
Daniel, thanks for sharing those tools, those animations,
yeah,
and of course, your very lovely research note. And it'll be really exciting to see this field of looking for those kind of resonance as we come up into the future, and as you mentioned with VRO. So very nice.
yeah. There's a lot to learn about the outer solar system
Yeah,
over the coming decade, and
that makes
yeah,
it exciting. Things to find.
yes, yes, yes.
Very cool. All
Yeah,
righty. That'll do, everyone. And I hope this made your outer solar system day just a little bit better. And we will see you on the next one. Bye bye.
yeah. Bye.